Section 2.3, the composition of functions. Okay, I promised that functions were the new numbers. Well, here's another instance of what I'm talking about. Last section, we talked about adding, subtracting, multiplying, and dividing functions to create new functions. And these new functions had their own list of inputs and outputs and domains and so on. Okay, well, we're going to talk about composite functions today. Okay, and so what a composite function, or at least the notation for that, looks a lot like the multiplication one, okay? But let's not get these confused. This circle right here, I like to read it as the word of, okay? So don't think about that as like a multiplication dot. That is an O, okay? It's an open circle here. All right, so anyway, f of g of x is exactly that. We're taking one function and we are plugging in another function inside of it, okay? F of g of x. Right? You plug numbers into functions. Well, now you can plug functions into functions. Why not? Especially if they're just the new numbers, right? Okay, so what is that going to look like in practice? Well, let's do some examples. Example number 1. Let's say we have f of x is 3x plus 1. And let's say that g of x is x squared minus 2x minus 6. Let's find g of f of x, and let's find g of f of negative 2. Okay, so that's going to be two things we're going to find. All right, so first of all, g of f of x means that I have the function g of x, and inside of it is plugged in f of x. Okay, so f of x is plugged inside of g. What does that look like? Well, that just means start off with g. Okay, start off with g. And instead of an x, leave a blank for all those x's. Okay, leave a blank. I like to put parentheses and just leave them blank. So x squared minus 2x minus 6. Okay, that's the function g. And what did I promise, right? I promised that I was going to plug in f of x into those blanks. In this case, f of x is 3x plus 1. Ah, look at that. Now I have a composite function. Let's simplify it, okay? So 3x plus 1 squared. That's something that we need to do first. That's just, oh wait, nope. There we go. That's just 3x plus 1 times 3x plus 1. We'll deal with that in a second. Let's distribute this negative 2. Negative 2 times 3x is negative 6x. Negative 2 times 1 is negative 2. Minus 6 here on the end. Okay, so 3x plus 1 times 3x plus 1. 3x times 3x is 9x squared. 3x times 1 is 3x. 1 times 3x is 3x. 1 times 1 is 1. Minus 6x, and hey, don't forget these two can be put together. That's negative 8. All right, and then like terms, so I have 3x plus 3x, that's 6x. And then, oh, wait, let me go further than that, right? 3x plus 3x is 6x. Minus 6x is 0. They canceled each other out. Okay, so all that's gone. And then I have 1 minus 8, and that's negative 7. So 9x squared minus 7 is g of f of x. Okay, so there we go. Now, remember, the second part of this question was to evaluate the function when x is negative 2. So I have actually a couple of ways to do that. Again, I'm trying to find g of f of negative 2. I can just plug it in, right? Substitute negative 2 in for x. Negative 2 squared is a positive 4, so that's 9 times 4 minus 7. 9 times 4 is 36. Minus 7. 36 minus 7 is 29. Okay, 29. So that's one way to do it, okay? And this way is good if you have the composite function. If you went and you found this formula, then by all means use it, right? But let's say you didn't have to find this part and you didn't feel like it, so you kind of skipped it. Okay, you actually can still work this problem out without it. Okay, again, we're trying to find g of f of negative 2. And I have to remember what that means. G of f of negative 2, right? So what I can do is just figure out somewhere else, what is f of negative 2? Okay, well, remember, f was 3x plus 5, so we have 3 times negative 2 plus 5, right? Let me make sure. Oh, no, it's plus 1. I'm sorry. Plus 1. Good thing I double-checked there. Okay, and then 3 times negative 2 is negative 6. Negative 6 plus 1 is negative 5. So f of negative 2 is negative 5. So I can actually just go ahead and scratch that and put negative 5 in its place. Let me clean that up a little bit. That's actually just going to be g of, negative 5. Well, can I figure out g of negative 5? I mean, obviously I can, right? So let's see. G of negative 5. Well, g was, I don't remember what g was. X squared minus 2x minus 6. X squared minus 2x minus 6. And in those blanks will be a negative 5. Negative 5 squared is a positive 25. Negative 2 times negative 5 is a positive 10 minus 6. 25 plus 10 is 35. Minus 6 is, lo and behold, 29, right? That was our original answer that we got earlier, right? So this way, the second way is actually easier if you don't feel like finding the whole formula. However, if you have the formula, just plug in the number. All right, so good times. Let's do another example. Let's say we have g of x is the same as before, x squared minus 2x minus 6. And let's say now we have a new function, h of x, and it's equal to x cubed. All right, x cubed. And I just say find h of g of 3. Okay, I didn't tell you have to find the formula, the composite function, right? I didn't say find h of g of x. I just said find h of g of 3. This is a case where it'd just be easier to say, okay, h of g of 3 is the same thing as h with g of 3 plugged in. So off to the side somewhere, I can find g of 3. That's 3 squared minus 2 times 3 minus 6. 9 minus 6 minus 6. Negative 3. So, okay, h of negative 3. Well, h is x cubed, so I can say, all right, well, h of negative 3 then is negative 3 cubed. Negative 3 times negative 3 is 9, times negative 3 is negative 27. Okay, so you see it's easier in some cases just to kind of work it out directly instead of finding the whole formula and then plugging it in. All right, let's do a few more examples. Example 3. All right, and this time, well, let me write the question first. F of x is equal to 3x minus 2. G of x is equal to x squared plus 5. So the question here is to find, let's say part A, f of g of x and find its domain. Okay, so first of all, let me talk about how to find those domains, right? Okay, so just like in the last section where you look to see where they overlap, we're going to actually do something kind of similar, all right? What you should do is first recognize, let me write this out, first recognize that this is f of g of x. So g of x is being plugged inside of f of x, right? G of x is plugged inside. G of x is kind of like the domain of f of x. Okay, so what I need to do is find the domain of that inside. So in this case, g of x. Okay, find the domain of g of x. Okay, let's look at g of x and think about that. If I had a number line representing all the numbers I'm allowed to plug in, I look to see if there are any fractions where I could possibly get 0 in the bottom. Don't have any of those. I look for any possible way I can get square root, like a negative under a square root. I don't have any square roots, so that can't happen either. So this graph right here represents the domain of G. Okay, I could write it out in interval notation, although for what we're trying to do here, you don't have to actually take that step. All right, so the graph itself is fine. So you find the domain of the inside function first. That's the first thing you should do. Second thing you should do is check the new function for restrictions. In other words, make sure there's no way you can get 0 in the bottom or any square roots. Okay, let's see what the new function looks like. F of g of x. So f of x is 3x minus 2. G of x is x squared plus 5. Okay, look at that. Distribute the 3. 3x squared plus 3 times 5 is 15 minus 2. So we have 3x squared plus 13. So that's my new function, which is again part of the question, right? I want to find this. Do I see any restrictions? Any way I can get 0 in the bottom of a fraction? Any way I can get a negative under a square root? I do not, right? So there are no other additional restrictions. So it just so happens that my domain, again, I steal the domain from above, right? I steal that domain. And if there were any restrictions, then I would go ahead and cut them out. But I don't have any. So turns out my domain is negative infinity to positive infinity. That was part A. Let's do part B, which is just going to reverse that. Yeah, I have room. Part B. Let's find g of f of x. Okay, so let's find the formula, and then we'll talk about the domain in a second. Okay, so g of f. So g with f of x plugged in. So this time that's x squared plus 5 with 3x minus 2 plugged in. Okay, and I'm going to quickly multiply this 3x minus 2 squared out. That'll be 9x squared minus 12x plus 4 plus 5. So that plus 5 will make that a 9. Okay, I know I did that quick, huh? There's a trick to it. I encourage you to go and try to figure out the trick. But okay, anyway, so that's going to be the function. Now I'll look at that and I don't see any restrictions that come, from there, right? There are no issues. That's perfectly fine. So let's check the domain of the inside function first, which is f. Remember, f is just 3x minus 2. And that has no restrictions, right? There are no fractions or anything to watch out for, right? I check it first, make sure I don't have any restrictions, and I don't. And so then the domain of the new one uses the same number line and it just adds in the extra restrictions if I have them. But I don't have any more. So again, negative infinity to positive infinity. That's going to be the case almost every time, by the way. All right, let's talk about one where that is not going to work out so nicely. Example 4. So this time f of x is going to be 6 over x, and g of x will be 1 over 2x plus 1. Let's find f of g of x and its domain. All right, so let's work it out. F of g of x. That means 6 over, Oh, gross. 1 over 2x plus 1. We need to simplify that. That's ugly. All right, it's actually not that ugly. Anytime you have a fraction embedded within another fraction, just remember that if you divide by a fraction, you just multiply by the reciprocal. So I'm going to take that denominator, flip it over, and make this a multiplication problem. Okay, so what does that look like? 6 times 2x plus 1 over 1. That's all that looks like. Okay, 6 times 2x plus 1 over 1. And why do I need that 1 on the bottom? I really don't, right? I could leave that off. So this is really just, let me try that again. 6 times 2x plus 1. Distribute the 6. And I get 12x plus 6. Somehow, I composed these two functions and I got something nicer to deal with. Let's talk about the domain. All right, so what is the domain going to look like? I look at the domain of the inside, right? The inside is G. So I look at the domain of G. It goes from negative infinity to positive infinity. But I could possibly get a 0 in the bottom, right? I have a fraction. Anytime there's a fraction where x is in the denominator, in the bottom, there's a potential for me to get a 0 in the denominator. What would cause that to happen? Well, 2x plus 1 equals 0. Subtract 1 from both sides. Divide both sides by 2. Negative 1/2. So negative 1/2, can't plug that in. That will give me 0 in the denominator. So that breaks my domain into two pieces. Let me just do it like this. Two pieces. The first one being negative infinity to negative 1/2. The second one being negative 1/2 to infinity. Now for the domain of the new function, I steal the old domain, right? The domain of that inside function from earlier. Go ahead and fill all that in. Okay, so I steal that one's domain because, again, that's the inside function, so I need to look at that one. And then I decide, okay, do I have any additional restrictions from this 12x plus 6? And no, right? I don't have a fraction anymore, so I don't have to worry about the denominator. I don't have a square root, so I don't have to worry about a negative under a square root. So this here is my denominator, these two pieces. First one, negative infinity to negative 1/2, union. Second piece, negative 1/2 to positive infinity. All right. One more thing to talk about. So one more example. Let's say we needed to do the opposite of compose, and this is called decomposition. In other words, I might have a function that's kind of complicated, and I want to write it as two separate functions. Let me write this out. So example 5, the final example. We are given h of x equals 1 over the square root of 3x plus 7. I want to find f of x and g of x such that h of x is simply the composition of f and g. Okay, in other words, I want to find out what these two are, that if I compose them, I get that, right? That's what I'm looking for. And the cool thing about this is there's an infinite variety of solutions here, okay? There's tons of answers. So some are more obvious than others, okay? So anyway, f of x and g of x. Remember, what we're trying to find is f with g of x plugged in. And actually, I'm going to go ahead and color code this one because I really think it'd be easier to see what's going on. So we'll say that red is f of x. I'll write that over here first. And blue is g of x. Okay, and so we're trying to find f of g so that I get the original problem, or the original function. Okay, so what does that look like? All right, that's the million-dollar question. What does that look like? All right, I think the best thing to do is to look at the original and try to identify g first. Okay, and I see a lot of different options right here. I think the easiest one that I see, though, is this square root of 3x plus 7. So I'm going to start off and say, I think this should be g of x. It's kind of a guess here. Okay, let me kind of, yeah, I don't want to have that box in. 3x plus 7. Okay, so if that is the case, I just took out that square root of 3x plus 7. I think the best thing to do here is to literally go ahead and like box it in or circle it or something and say, okay, that was g of x. It has to now be x. That's going to be my f of x. And then you can try it out. You can actually try that out. You can say, all right, f of g of x, okay, that's 1 over blank, and the blank goes g of x. Okay, how does that compare to the original function? Yes, that works. Okay, so that's one option. Let's do another option. Let's say, okay, g of x is not the square root of 3x plus 7. It's just 3x plus 7. Okay, what about that? Okay, well, again, all right, if 3x plus 7 is going to be g of x, that means that has to turn into just the x for f of x. So that leaves me with 1 over square root of x. Aha, you can check that one out too. It works. Now I'm going to do one more that I see, just because I see it, and why not? Okay, and so this last one here is going to be, there I go being OCD again, g of x. What if g of x is just this 3x part right here? Okay, replace the 3x with just x, and now you have f of x. All right, so any one of these combinations works. Plus there's others, right? I see other ones right now, but I'm not going to go ahead and write them all out. So there you go. That's decomposition. But overall, we talked about composing functions, finding the new ones, finding the domains of those new functions, little shortcut workarounds if I don't ask for the actual formulas, and yada, 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 yada.